The question was to sketch and set up the integral expression to find the area of a single petal. What were the important parts that we needed to know in order for us to be able to solve that question? We needed to know that the first petal was in the first quadrant. That's going to be assistive when we deal with our picture. Part of the reason why that's useful is it tells us that we're going to go, and the other thing we found is that we also saw that these R values are going to equal 0. Why did I want to set R equal to 0? At each of these theta values, 0, pi thirds, 2 pi thirds, my radius would go to 0, right? And what that would mean is that as I go through here, a radius of 0 is at the origin. So if I go from the origin and then I go out and draw and then come back, that radius would go out and then come back in and give us a single petal. So then, once we figured out where those are, it's really simple. We just set it up in our fraction that came from the sector formulas, 1/2 the integral from, we picked 0 to pi thirds. Does it really matter that I picked 0 to pi thirds? Could I have picked any other combination of numbers? Sure, I could have gone pi thirds to 2 pi thirds. I could have gone 2 pi thirds to pi. There are several options I have for that. It doesn't really matter which two. Why would I have picked 0 and pi thirds? What is the main reason why I would want 0? Because it's 0. And 0 makes life easier. Now, here's what I would like to point out. This is my little aside. All right? Here's my aside. For the full rows, if I want the full rows, what would I do? I would do 3 times the 1/2 the integral from 0 to pi thirds to sine of 3 theta squared d theta. Absolutely, yeah. I put it this way just so that I can see that I have the, this is completely an organizational choice, that I can see that I'm doing, so the question was, since I'm on the microphone, I should probably repeat the question. The question was, do we have to turn this into a, could we turn this into a 3/2? I am making a purposeful decision to not write it that way because I want to see that here is the area for a single petal and that I'm going to have 3 of them. So this is a situation where the symbolic nature of writing it is going to overwrite the mathematically clean nature of how I'm going to write it. Make sense? Awesome. And you'll see that I don't always do that. You'll see that eventually in the next question that I will abuse that system a little bit. Speaking of which, let's deal with the third one. So, let's talk about this. We want to sketch and set up an integral expression to find the area of one petal of r is equal to 4 cosine of 2 theta. Cool. Do not evaluate. Yes, I love the do not evaluates. What do we do? We know that the first petal is on the x-axis, and why do we know that? Because it's the cosine, we know that we're going to be centered on the x-axis. We also know that there are how many petals? Because 2 times 2. Even the even thetas will produce twice as many petals, and I believe I actually can graph that. So this was the 3-petal graph, and we saw that. Let me just animate it one more time for you all. Oh, I want to display. Dang you. Erase the traces. If I graph that, you saw that with the 3 petals, it doubled over itself between 0 and 2 pi. If I go down to the next one, and if I graph that with 4 petals, you can see that 0 to 2 pi, it doesn't actually do that weird double over effect, and that's what causes this to have 4 instead of 2. All right, so because this is a petal problem, what do I want to do to find my thetas that I want to use? Find the thetas for the single petal, which means I need to really find out when the r will equal 0. So I'm going to set r, which we know is this 4. Oh, you know what? I haven't drawn yet. and I went out to the 4, why? Coefficient is 4, so we have a length of, each one of these petals will be 4. All right, so r is equal to 4 cosine of 2 theta, which is 0, which means the cosine of 2 theta will equal 0, which means I want all the times that cosine will equal 0. The y-axis, perfect, no, that's great, I love that. Cosine equals 0 on the y-axis. Now I just have to remember which ones those are, right? So that's what? Pi halves, 3 pi halves, 5 pi halves, and I'm going to do something really weird here. Now just bear with me. I'm going to put negative pi halves. Are we okay? Is that actually going to equal 0? I'm going to put negative pi halves, and we're going to see why in just a minute. So negative pi halves is literally just going from 0 and going back to the negative y-axis. So that's still a 0. Why we're doing that? Well, we'll see in just a moment. Now that's 2 thetas that, which means my thetas are going to be negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, so on and so forth, going on forever and ever and ever and ever and ever. Do you agree with that? We cool with that? Yeah, it's a negative pi halves and a pi halves. We cool with that? Okay, cool. So if I want this, I'm going to pick 2 that are together. And the 2 I'm going to pick are going to be negative pi halves and pi halves. Again, I keep picking this negative pi halves, and maybe at this point in time, maybe some of you are still going, why the heck are you doing it? Maybe you think you know. We'll find out in just a minute. Area is very simple. Area is 1/2 the integral from, and I said I'm going to pick negative pi halves to pi halves of the r, 4 cosine of 2 theta. And this is perfectly fine, and you would not, and in fact, if I would have picked pi halves to, or pi fourths to 3 pi fourths, that would be correct. 3 pi fourths to, did I do anything wrong? Thank you. You should be fourths. Appreciate it. Negative pi fourths to positive pi fourths. We could do pi fourths to 3 pi fourths, 3 pi fourths to 5 pi fourths. It doesn't really matter which 2 I pick. And I keep picking this weird negative one. Here's the reason why I'm going to do that. Which number are we kind of obsessed with when it comes to getting as a limit of integration? I really like 0. 0 makes my life so much better. Well, if I go from negative pi fourths to pi fourths, that would be this initial drawing, right? And do you agree that really this is a beautifully symmetric shape over the x-axis? So instead of going from negative pi fourths to positive pi fourths, what's another thing I could do? What if I didn't want to go from negative pi fourths to pi fourths? What if I wanted to go from 0 to pi fourths? Well, that would give me the upper half of this petal, wouldn't it? And if I get the upper half of the petal, what could I do? If I multiply it by 2, now I've done what? If we use the symmetry to make the limit go to 0. So what I can do is I can say, well, what if I double my integral and I change my limits of integration to 0 to pi over 4 of 4 cosines of 2 theta squared d theta. Then what does my integral, then what does the full thing become? Well, the 2 and the 1/2 would cancel each other out, and I'd just be left with the integral from 0 to pi fourths of 4 cosine 2 theta squared d theta. And suddenly I get out of having to calculate a negative pi fourths. I suddenly can calculate at the 0. And what you're going to see me consistently do throughout the remainder of polar is if I can use symmetry to create a 0, then I will do it. Now please note, I'm not going to use all the symmetry that exists in the problem, but I will be consistent using the symmetry to create a limit of 0 in my problems. Cool? Cool. As an aside, what would this be if I wanted this to be the full rows then? Yeah, for the full, well, be careful. Times 8 if we're using which equation? The 1/2. This is the area of one petal. So if I wanted the full rows, I would only have to multiply this by 4. And again, you'll see that part of the beauty of this is that now I don't have to really think all that hard. I don't have to deal with questions like, what is a full period and how do I get from this to this to this? I can just look at this question and go, hey, let's just find one petal, ignore the whole period thing entirely, and then just use symmetry to be able to answer my question quickly and efficiently. Now, someone had their hand raised. Someone had a question. The picture, one more time. Where would you like me to start it from? Would you like me to start from the negative pi over 4? So if I start, this is actually going to start drawing from negative pi over 4, and then it will draw all the way through, should draw all the way through pi over 4. I draw it at 0, so just be aware of that. So negative pi over 4, you can see that from negative pi over 4, it will draw this little bottom part, and we do it. If I wanted to draw this, say, so if I draw from negative pi over 4 to just pi over 4, it draws that one petal. And essentially what I'm doing in this question, I wish there was a quicker way to do that, is I'm going to say, well, if I draw just that little piece, and I find the area of this piece, then I double it, will find me the bottom half. Then if I multiply that by 4, that gives me everything I want, which is pretty darn cool. And you're going to see us abuse all of that thought process a lot as we go through these questions. All right, day 3. Oh boy. This is where things get fun. All right. So what we've done in day 2 is literally just look at the problems where we're looking at a single equation. Now what we're going to do is we're going to start sketching a couple of different graphs at the same time. All right? So let's take a look at this right now. We're going to sketch and set up an integral expression to find the area inside the graph of 3 sine of theta and outside of the graph of r is equal to 2 minus the sine of theta. Which means we need to be able to graph these. Now, one of these we're going to have to actually know the graph of. The other one we can just kind of we're going to have to do the whole like theta thing. So we've got some options. We can either create the tables for these. In fact, why don't we create the tables for both of these? Let's just have some fun. So this is going to be 3 sine theta, and this is going to be 2 minus the sine of theta. Let's just create them. Again, we're going to use our thetas as 0, pi halves, pi, 3 pi halves, and 2 pi. So what is this? What is 3 sine of 0? Sine of 0 is 0, so this would become 0. Sine of pi halves would be 3. At pi we would get a, at 3 pi halves we would get a, at 2 pi we'd get a. Okay, let's talk about graphing this one real quick. So, when we're going at positive x-axis, we have a radius of 0. We're on the y-axis, we have a radius of 3. When we're at the negative x-axis, at pi, we have a 0. Okay, that's this point again. At 3 pi halves, the negative y-axis, we have a radius of negative 3. What the heck does that mean? It means that this is going to be in this direction, but we're going to go in that direction backwards 3, which is that point up again. Bingo. Because we're going, okay, I'm looking in this direction. Essentially, imagine your theta being which direction you're looking. So I'm now looking this way, but then it says go -3, which means walk backwards 3. Okay, congratulations, folks. We have 2 points. Why? What does the graph of 3 sine theta look like? It's a circle that has a diameter of 3 that's on the y-axis. And this is one of the shapes that you really kind of just need to know. I wish there was a better way to tell you that. But this is one of the shapes we really need to know. And when you get a shape that does that, it's a circle that is going to go through there. On the flip side, we have a much more interesting graph in 2 minus the sine of theta. So again, sine of 0 is 0, so this is 2 minus 0, which is 2. 2 minus sine of pi halves is 1, so 2 minus 1 is 1. At pi, this will be 2. At 3 pi halves, so 2 minus -1 is 3. And then 2 again. So let's graph those points. 2, 1, 2, 3. So we get a shape that looks something kind of like that. It doesn't cardioid because this is bumped out a little bit. So the only time you'll get the heart shape is if this happens to go through 0, 0. That help? So if it's at 0, 0, it makes the heart. If it goes out, then it will make this kind of like squished circle look. And if it gets bumped too far in, it will make a loop. Yeah, so you can get weird loop things that happen in there too. And we'll see one of those. Okay, what region are we trying to find? Yeah, well, it's not actually here. If you look, it's inside of the blue, but it will be outside of the red. So that's actually, I would suggest very lightly drawing this because I'm going to make some radial lines to assist you. So we're trying to find the area of that region. How the heck are we going to do that? So one of the things to think about is as we look at this, first thing I notice is that we've got some intersecting points, right? And do you agree that if we were to look at these, and if I draw lines through those intersecting points, we'd be looking between these, and we could call that like an alpha, and we can call that like a beta, right there? And what's going to happen is that between those points, I don't want to have this region at all, do I? I want to take this and find the area from here to here, because that would give me all of that, right? But then if I look, I really want to take the area that would happen inside the blue and then do what? Subtract the area that would happen inside of the red, right? And what would happen is we'd get a bunch of different radiuses. And ideally, I'd really just want to kind of realize that as we go, I really just want to kind of take this blue piece minus this red area, and that would give us our thing. So what do I really need to find then to be able to set this up? So if I'm really kind of breaking this whole thing down, what I really want to do is I really want to find the integral. I really want to find the area created in the blue piece between alpha and beta in what's setting up the blue. That was the 3 sine theta squared d theta. And I want to subtract from that between the same 2 points So do you agree that this is kind of what we're looking at doing? And does that make sense? So what's the only thing we have to figure out now? The only thing I don't know is alpha and beta, right? I mean, I've literally got the entire thing set up. I just need to figure out between what two angle measures. So how do we do that? Right, and this is awkward silence. Area of a sector is what we just set up here. Basically, I said let's find the area of the blue sector minus the area of the red sector. Because if I find the area of this blue piece between alpha and beta, do you agree I'm going to find really everything between here and here? Well, let me see if I have a picture that I can use to assist you in this. Essentially, what I want to realize is I want to figure out where those two intersection points are. What the devil is that thing doing? I wonder why it does it that way. Edit, no display. So essentially what I want to realize is, oh, why are you graphing like that? Let's graph the whole thing. So there's that circle, right? And then here is, let's just animate that whole thing. Let's get you back to here. So what I need to find is I need to recognize that between here and here, I need to really figure out what those 2 points are, don't we? So how do I find out what those 2 points are? Right, those are intersections. Just like everything else in math, we set the intersections equal to each other. So let's do that. Let's set these intersections equal to each other. So if I set 3 sine of theta equal to the 2 minus the sine of theta, then really what are we trying to do? We're trying to figure out when is 4 sine of theta equal to 2? When does the sine of theta equal 1/2? So when is sine 1/2? Pi 6 and? And I don't really want to mess with any more pi 6, so let's say pi 6 to 5 pi 6, right? So if I go back to my cool little picture, let me get to pi 6. If I were to graph this between 0 and, let me graph number 1. Hey, there we go. That's pi 6 to 5 pi 6. Agreed? So if I graph between pi 6 to 5 pi 6, if I do the blue, that would give us the entire region of this, right? And then if I subtract the red region from that, that would take away this piece, and that would just give us this cool little blue region, and we'd be good to go, right? So ladies and gentlemen, let's just write that down. So this is going to equal 1/2 the integral from pi 6 to 5 pi 6, which if you look, pi 6 is definitely the alpha line, and 5 pi 6 is definitely a beta line. 3 sine theta squared d theta minus 1/2 the integral from pi 6 to 5 pi 6 of 2 minus the sine of theta squared d theta. Now you'll notice, could I possibly have used some symmetry here? I could have actually gone from pi 6 to pi halves. There's symmetry there. Why did I not do that? It's not a 0. It's ultimately what it always comes back to. It's not a 0, so screw it, I don't want to do it. And that's what we're going to base everything on. Not bad? Luckily it says do not evaluate, because no. The other thing I do want to point out is I wrote this as 2 separate integrals, but I do want to point out I could factor the 1/2 out, and you'll notice that these have the same limits of integration. So I could have actually written this as angle which should start kind of reminding you a little bit of volumes of rotation. If you know that this is going to mess you up, my suggestion is write it as two separate integrals and recognize it as two separate integrals. All right, here we go. Not too shabby? All right, let's graph this next one. Do we know what 3 cosine of theta looks like? Circle on the x-axis. If you're not sure about that, we could totally do this as a theta. We can totally call this 3 cosine of theta. We can totally call this 1 plus the cosine of theta if you don't believe me. 0, pi halves, pi, 3 pi halves, 2 pi. That's great. This will be, the cosine of 0 is 1, so this is 3. Cosine of pi halves is 0, so this becomes 0. At pi, this is a negative 3, 0, and 3. Cool. So we've got 3, 0, negative 3, 0, 3. Which gets really dumb. But again, if you start realizing you're just bouncing between the 2 points, you realize that that's going to have to be a circle. It's a really crappy circle. What about 1 plus cosine of theta? So this will be 2. Let me do this in blue so that I have 2 different. 2. This will be 1. 0, 1, and 2. So 2, 1, 0, 1, 2. So what shape is this going to be? This is our heart. So we go whoa, whoa. Whoa, that brought that heart shape out way too much. This should really curve more. What the devil am I doing? All right, cool. What am I trying to find? I'm trying to find the area that is literally completely encased. So I want the common interior. The common interior is that region. Agreed? Now this is where my little picture thing is going to play a very important role. All right, here we go. As we can see, this is a very good shape. Whoa. And we're looking for this cool spot that kind of overlaps, right? So this is where things get a little bit sketchy. So we go through, we would come up. What happens right here? There's an intersection, right? And at that intersection, if we're looking through this particular shape, it'll be a little bit easier here. This is this section between here and this spot. Between this point and this point, what's defining that edge? The blue or the red? The blue. What happens after that? The red is going to define this edge between here and here. Also, do I want to deal with this as the whole shape, or would I like to use symmetry? Okay, we're going to use symmetry. By the way, hopefully you're starting to catch, when are we typically going to use symmetry? Cosine. Cosine we like because cosine abuses our symmetry. Okay. So what I'm going to have to do is I'm actually going to have to find two things. I'm going to have to find this between, with the minus, yes, okay. I'm going to have to go from here to this intersection point using the blue line, and then from the blue line, I'm going to have to go from here to from this intersection point, I'm going to have to use the red line from here to this point. Do you agree with that? So there's a changeover that's going to happen. So my question is, where on earth is that point? That's the intersection, right? So let's find the intersecting point. This is 3 cosines of theta is equal to 1 cosine, 1 plus the cosine of theta. Subtract this. This is 2 cosines of theta is equal to 1. We want to know when the cosine of theta is 1/2. What are my thetas? Pi thirds. Five pi thirds. There is a 7 pi thirds that will occur. Yeah, so it's like 1, 5, 7, add 4 to that, or add 6 to that, 11 is going to be the next one. The other one I'm going to include in here, of course, is negative pi thirds. Cosines also get that weird negative. Why does the negative show up? Because at the end of the day, we're going to utilize 0. So what I'm going to do is I'm going to find the top half of this shape. And why am I going to find the top half? Because I'd really like to incorporate the 0 here, find it going over to here, and then I'll just multiply by 2 and call this a day. So what I want to realize is that this area for the top half will be 1/2 the integral, right? And my first point is going to go from 0 to pi thirds. And from 0 to pi thirds, what is going to make this shape? The blue region, right? So from 0 to pi thirds, that is going to be defined as the blue, which is which one? The 1 plus the cosine of theta or the 3 cosine of theta? That's the 1 plus the cosine of theta squared d theta. Then what do I have to do? This is an addition, because now I need to add on this last section, right? So I'm going to add to that 1/2 the integral from where to where? Pi thirds. And why am I starting at pi thirds? What's happening? We got it now? There we go. And for you who are going, wait, I'm confused by that, let me see if I can make this actually graph what I want. 0 to pi thirds. So far, so good? So from 0 to pi thirds, I want the blue piece, right? So when do I go from pi thirds to this? How am I going to get from pi thirds to this spot? What is that angle measure going to be? When does the red hit this region first? That's pi thirds to pi halves. And I want this to change over from the blue, which goes on the outside. Now I want it to change over to the red. Agreed? So what I'm going to do is I'm going to call this pi thirds to pi halves. Are we okay with that? And we're going to use 3 cosine of theta squared d theta. We cool? And do you agree that that will sweep from here all the way over to this piece? And since that works, that's the top half. If I want the whole region, then what do I need to do? Then we just need to find 2 times the area, right? 2 times this area. And ultimately what's going to happen is we're going to get rid of the factors of 1/2. By the way, can I write this as a single integral? These are not the same limits, so we are stuck writing this as 2 pieces. Whoa! And what's the only difference between whole region and top half? Since we doubled, the factors of 1/2 cancel. I use 2 L's on cancel, I don't know. How do we feel? Not bad? So, just like when we're dealing with areas of regions, we're going to have to deal with additive versus subtractive regions. And this is where a picture really plays a incredibly important role. Because without the picture, it's hard to tell, should I be subtracting or should I be adding? You know, and we have to start making sense of common interior, which is combined, versus inside of one shape and outside of the other. It is a lot. Any questions? I will stop there.